Questions about anything? So the exam 2 take-home exam will be released on Gradescope at 5 o'clock, 5 p.m. today. I also posted on the homepage at that time. And it'll be due Friday at in Gradescope by 11 p.m. Are there questions about anything? Let's see, there's a couple things I wanted to mention about the section on the fundamental theorem of calculus. Something to note is you might notice that when the book talks about continuous functions, they allow for a finite set of points where the function is not continuous. So here's a fact. Suppose f is continuous on a closed interval except at perhaps finitely many points. There could be no bad points, except at finitely many points. E is a finite set. Then f is Riemann integrable. So let's see, there's some, I can draw you an example of that. Easy one would be something that has a jump discontinuity. So let's see. Here's A, here's B. And then who cares what this thing is? It could be in the middle somewhere. Has a jump discontinuity there. It's continuous everywhere except that one. And then when you realize if you can show that that thing is Riemann integrable, you could add points one at a time until you got a finite set. But here's another example of a we've seen. Let's take this famous example of sine 1 over x. Sine 1 over x wiggles like crazy between plus and minus 1. There's plus 1, there's minus 1. And sine 1 over x goes totally bonkers up and down. Let's see, it's negative. I mean, it's a odd function, so this is sine 1 over x. That's continuous everywhere on the interval, say, from minus pi to pi, and has a terrible singularity at the origin. Oops, I should add. Suppose f is continuous and bounded, I should have added. Continuous and bounded. That's an important thing to add. Let's see. Okay, let me fix this. It's important that f be bounded. It's continuous on AB except at finitely many spots. So, back. Let's suppose f is bounded. On AB. And f is continuous on AB, except perhaps at finitely many points. Okay, there's a jump discontinuity one, and here's a terrible discontinuity one. At least it's bounded, though. If I made it like 1 over x times 10 to 1 over x, that would have gone totally, it would have been unbounded. That would be bad. So this is bad, but still it's better than something that would be unbounded. Sine 1 over x is continuous on, let's say, minus pi to pi minus the origin. And it's bounded by 1. In absolute value. Okay, so we're going to show that these things are Riemann integrable. So the proof of the fact, it's going to be easy. Picture proof. Let's see. It's enough to do this one, adding 1 point. Add a single point. Then we can just add them one at a time. Of discontinuity. Okay. So let's suppose that f of x is less than or equal to m, so it's bounded, and f is discontinuous at c. Okay, so here's the trick. Let's let epsilon be bigger than 0. We're going to use the Cauchy criterion to see that f is Riemann integrable. So use the Cauchy criterion, which remember is we need to find a lower sum, a partition, P, such that the upper sum minus a lower sum is less than epsilon. So remember, the upper sum is like an area above the graph, and the lower sum is it's more than the area. It's the area of something that's above the graph, and the lower sum is the area of something that's below the graph, rectangles, mate. And if we can squeeze those in with an epsilon for any epsilon, then the area makes sense. Because remember, the area would be the sup of the L's or the inf of the U's, and those would be equal. Okay, so I need to show that I can do this, and here's the picture proof. I'll have a function. It's nice. From A, C it goes bonkers maybe. And then it's nice to B. So C is a bad spot. Could have a jump, or it could have a really hairy discontinuity. But at least it's bounded near there. So I let epsilon be bigger than 0. Let's see how I'm going to think about. I'm going to take a little delta here. Here's C minus delta and C plus delta. So this is C minus delta, and that one is C plus delta. And I'm going to take an upper sum like that. Here's plus m. And a lower sum, let's see, I don't know what the plus m is. I'll make the m here. It's bounded by something. then the integral, so here's the deal. I can see that I can make an upper sum on that integral so that that the integral from c minus delta to c plus delta would be less than or equal to m times 2 delta. So here's the plan. We're going to get upper sums and lower sums such that the integral, let's see, we're going to have we're going to get the integral from a to c minus delta. Let's have a lower sum from a to c minus delta. That's going to be less than or equal to the integral from a to c minus delta of f dx, and that's going to be less than or upper sum for that, a partition for that integral, c minus delta. And those are going to be within epsilon over 2 of the actual. So these are going to differ by less than epsilon. Let's make it epsilon over 3. So these are going to be differ by less than epsilon over 3. And we'll do the same thing for the other side. Same for the integral from c plus delta to b. Okay, and then if you think about that little, the one in the middle there, I would have that soup. Let's see what I would have. Inf of f over that little interval, c minus delta times c plus delta times the 2 delta, that's the width of that thing. And that's less than the soup of f over that same interval. Times 2 delta. Okay. And that's less than minus m times 2 delta. And this is less than plus m times 2 delta. And so if I add those to my other two lower sums and upper sums, my deal is I want to make these, the difference I want, let's see, m times 2 delta minus m times 2 delta to also be less than epsilon over 3. And so you can see how easy it would be to get that. This thing right here is 4 delta m. And so the aha is I need take my delta to be equal to epsilon over 3 divided by 4m. And then I would get a partition where the upper sum minus the lower sum is less than 3 times epsilon over 3 is epsilon. So that's a standard thing when you're dealing with a spot that's nasty when you do integration. Because you can make if it's bounded, you can make the interval so small that the area would be a small delta times who cares bounded height of those rectangles. And so they become sort of immaterial. How weird the behavior is there. Questions about that one? Well, here's the fancier version of the fundamental theorem of calculus that I wanted to tell you about. Of the fundamental theorem of calculus. If f is piecewise, I'm going to define this in a minute. If f is piecewise C1 smooth on AB, then the integral from a to b of f prime of z dz, is equal to f of b minus f of a. Okay, and so what I mean by piecewise smooth, I mean the function can have kinks but no jumps. So here's a definition. So piecewise smooth allows kinks in the graph, but no jumps. That's the way I like to think about it. Of course, that's not a mathematical definition. So let's see, the mathematical definition is we would partition AB into subintervals. Okay. We call this one x. A is x naught, B is xn, and this would be x1, x2, etc., just like a partition. Dot, dot, dot. And when you graph the f, it's got to be continuous. So here's my graph of f of z. Here's A, here's B. F could go like this, have a kink, go like that, have a kink. And it doesn't have to be straight lines, so let's go kink, line, kink, etc. So this means that f is continuous. F of x is continuous on each of the intervals on xn minus 1 to xn, and differentiable on there, and the derivative is continuous. And f prime exists on that closed interval, meaning up to the edges. The values of the f's have to hook up. Values of f hook up, which means the limit as x tends to xn from the left of f of x equals the limit as x tends to xn from the plus hook up. But the derivatives don't have to hook up, so they can have corners. That's what I mean by kinks. But the values of f prime don't have to hook up. Well, then the fundamental theorem of calculus still holds. And it's an easy thing to see. Here's the proof. The integral from a to b of f prime dx would be a sum of the integrals over those subintervals. The f primes exist in our continuous up to the ends, they just might not hook up at the ends. And so this would be a sum as n goes from 1 to capital N of the integral from xn minus 1 to xn of f prime dx. And since I have an interval where the f is continuous and the f prime exists and is continuous up to the edges, that's the basic version of the fundamental theorem I showed last week. That's going to be a sum as n goes from 1 to n of f of xn minus f of xn minus 1. And that's when you realize, aha, that's a telescoping sum. Because those things hook up, we're going to get pairwise cancellation. So let's see, that would be f of x1 minus x naught plus f of x2 minus x1. That's going to kill the x1 term. The next one's going to kill the x2 term. Etc., etc. So plus dot, dot, dot. What's the second to last one? That would be f of x n minus 1 minus f of x n minus 2. And then the very last one would be plus of f of xn minus f of xn minus 1. Okay, so let's see. We get this one gets killed by this one. This one gets killed by this one. X3 would get killed by the next one, etc., etc. This one's killed. This one would be killed. Let's see. This one gets killed by which one? No. This one kills that one, etc. This one would get killed by something else. And everything gets canceled out there, except the very first one and the very last one. And so it's f of xn minus the first one. Check. Okay. I didn't want to make a big deal out of that at the time because if you understand it for an interval, then you certainly understand this argument here. Questions about that one? Okay, so that we can start working on chapter 8 now. It's not going to be a hard subject to talk about at all. So chapter 8 is the last thing we're going to do. We're going to do 8.1 through 8.3 and call ourselves done with the course. 8.3 is a wonderful section on the exponential function. So it's kind of like frosting on the cake. And 8.1 and 8.2 are rather straightforward. So let's see. This is going to be about sequences of functions. And an exciting moment in your mathematical education is when people start talking about functions like points. So an exciting moment is we can start thinking about functions as points. About functions. And the really fascinating thing is you want to think about what are coordinates for functions. And the answer to that question is Fourier series. So we can think of functions as sort of an infinite dimensional Rn. And the coordinates are going to be the Fourier coefficients as points. I'll put points in quotes. Points in a space. Okay, last time I explained uniform continuity. We're going to talk about, let's take CAB is going to be equal to continuous functions on a closed interval. And so the functions in that space are going to be our points, and the distance between two functions in that space, f and g, is going to be, well, let's see, since they're continuous, we can take the max of f minus g, absolute value, when x is in AB. That's the distance between those functions. And uniform, let's see, last time I talked about uniform convergence. Remember what it meant? We say that Fn, I like to write Fn converges uniform. I put a double arrow there to F on interval AB means given an epsilon bigger than 0, there is an n, a positive integer n, there's capital N, which is a natural number, such that Fn of x minus f of x is less than epsilon, and here's the key, uniform for all x in AB. Okay, so that's what the uniform means for all x in AB. That's what uniform means. When the x is, when the n is bigger than n, when little n is bigger than capital N. I guess greater or equal would be okay. Okay, and notice that distance I just defined. It means that the points, if you think of the functions as points, then their distances go to 0. So, interesting note, same as saying that the distance between Fn and f is less than epsilon. And so if you think of functions as points, and that as a distance, it means that Fn converges to f as a sequence. Converges, so this is quotes. When you start getting good at thinking like this, you can think of those things as points. Fn tends to f in this space of continuous functions in that distance as a sequence. Of points where we use that distance instead of the usual distance of points, using the metric the distance between Fn and f. Okay, that way of thinking is leads to all kinds of discoveries. It means if you understand basic definitions in terms of regular distance, suddenly all those definitions make sense in this new setting. And this turns out to be a complete space, just like the real scenario. Every Cauchy sequence has a limit, etc. Stuff like that. So once you establish that all the normal things you talk about are true for a new space like this, suddenly you have all the theorems you ever proved are also true. That's exciting. Another very exciting space is integrable functions, where you take the distance to be the L2 square integrable distance. That's Hilbert invented that when he started inventing Hilbert space. It's a very exciting space with a lot of interesting properties. It's also where it was discovered that the Riemann integral is not sufficient to be able to understand that space. That space requires the Lebesgue integral. Okay. Anyway, I'm not going to get bogged down in hyping this exciting moment. I just wanted you to be aware of it. We're going to do some of the basic facts. Let's see. Let me make another definition here. Definition. A sequence of functions that are continuous on a closed interval is called uniformly Cauchy. And you could guess what the definition is. If, given any epsilon bigger than 0, there is an n such that fn of x minus fm of x is less than epsilon. And here's the uniform part for all x in AB. So that's a uniform estimate. When the n and the m are bigger than capital N. Okay. Okay, here's big fact number 1. I'm going for 3 big facts in the next couple days. I'll call this big fact number 1. Uniformly Cauchy sequences of functions converge uniformly. Uniformly Cauchy sequences of functions on a, let's see, uniformly Cauchy sequences of functions, I'll say in the space of continuous functions on AB, converge uniformly. Okay, this turns out to be a no-brainer. So here's why. Okay, if let's suppose we have this uniformly Cauchy sequence. Suppose Fn is uniformly Cauchy. Then if you think about it, that estimate above, Fn of x, is a Cauchy sequence for each x. Okay. So it converges because we know R is complete. R is complete, meaning each Cauchy sequence converges. So Fn of x converges to something. Let's call it f of x. Okay, now my next claim is that Fn of x converges uniformly to f of x. Meaning I get the same estimate Okay, that's an easy thing to see just from the definitions. So let's epsilon be bigger than 0. All I know is the fn's are uniformly Cauchy. So then there is an n in the natural numbers such that Fn of x minus Fm of x is less than, how about epsilon over 3? When n and m are bigger than or equal to, let's say, capital N. Okay, so what am I going to do here? Now a standard trick. Let's see. I'm going to pick f of x minus Fn of x. I'm going to do that's equal to f of x. I'm going to subtract minus an Fm of x plus Fm of x minus Fn of x. And that's going to be less than or equal to f of x minus Fm of x plus let's see, what am I screwing up here? I got myself turned around backwards here. Oh, blast. Oh. Okay, let epsilon be bigger than 0. Before I did that, I should have said pick an x in AB. I need to show that fn of x minus f of x is small when n and m are bigger than or equal to n. Okay, so I picked an x. I have this estimate. I can make this one less than epsilon. Epsilon over 3 is what I said, but I should have said epsilon over 2. And now I picked my x above. And I know that fm of x tends to f of x. So at this moment, my n is, I can let the m go to infinity. So in fact, I can now take a gigantic m here. Take a gigantic m. So that this is as small as I want. Epsilon over 3, 2. Okay, so the deal is I can do that, and then I get that this x I get that f of x minus fn of x is less than 2/3 epsilon. So epsilon over 3 plus epsilon over 3, which is less than epsilon, when n is bigger than or equal to capital N. Okay, so the deal is I have this uniform estimate, and then I can let one of the m's go to infinity, and while I hold the other one fixed. And you see, when I picked just an arbitrary x up there, I just did this for one of the for one arbitrary x, and I get the same estimate for all x when so I should point out here that x was arbitrary. So I get the uniform convergence. My fancy notation for that is a double arrow convergence. On AB. My next big claim is that that limit function is also continuous. So big fact number 2, the limit function has to be continuous. So must be continuous. 2. And so if I go back and look at my demonstration up there, let's pick a C in AB. Here's the standard trick. I'm going to look at my limit function, f of x minus f of c. I do that standard trick. Let's see. What am I going to do? I'm going to write that same thing. I have f of x. I'm going to subtract minus fn of x plus fn of x Okay, now I have to, that bugs me, that x, I've got x's and c's. Now I realize, aha, I can also add fn of c minus fn of c let's see. I want to subtract minus plus. And then minus f of c at the end. Three things in the middle there. So I'm adding and subtracting things that don't change the value. And when I put them together, I realize, aha, I can make all three of those things as small as I want. So this is less than or equal to f of x minus fn of x. I can use the uniform convergence to make that one as small as I want. Then I have fn of x minus fn of c and then finally I have fn of c minus f of c. Okay, what am I trying to see? I'm trying to see that f of x is continuous. Can I make all three of those things as small as I want? So I think I'm going to think about, rather than cram this in the last minute here, let's think about how we can make these three things small. This one's the easy one. That one we can make less than epsilon over 3 by uniform convergence. We know that each of our functions is continuous. Let's see. Oh, this one can make small by uniform convergence too. What am I doing? So this one is also an easy one. So that one also would be less than epsilon over 3. And this one, I know that the fn, so here's where I have to think. Aha. Let n be equal to the big N. What am I doing? I'm going to save it for next time. Okay, so I can choose an n big enough so that those are small, and then I fix the n. So, and then I know that, let's say, I'm going to let n, little n, be equal to the big N1. So it's fixed. And then I know that the fn in the middle there is uniformly continuous. F sub capital N is uniformly continuous. I guess I know it's continuous. I don't know it's. I know fn is continuous. And then I can get the middle term. By taking x close to c. So I get the middle term is small when x minus c is less than delta. I'll do that more carefully next time. Okay. That's enough for today. Sorry for getting